In this video, let's look at another behavior of functions, which is concavity. So we define concavity as let f be differentiable rather on an open interval I. The graph of f is concave upward on I if f prime is increasing on the interval and concave downward on I if f prime is decreasing. So for us to easily understand that, let's zoom in here on our figure here. When we say when we say f prime is increasing, this is what we mean. The first derivative, the slopes are going up, and this is concave upward. It's characterized by U shape, something that is U shape. You can also have a decreasing function that is concave upward. You can have it something like that. There. This is concave downward. On the other hand, the first derivatives are going down in inverse U shape. But you can also have an increasing concave downward function that would look like this. So, how do we now determine if in that interval a function is concave upward or concave downward? We have what we call the second derivative test for concavity. Let f be a function that is differentiable on some open interval containing c. If f prime of c is greater than 0, then the graph of f is concave upward. If it's less than 0 or negative, the graph is concave downward. Now, of course, there will be parts of the graph where the concavity changes, and at the point where it's concave upward to downward and vice versa, that point where the concavity changes, like here, here, and here, that's what we call a point of inflection, or POI. So for us to be able to know whether there's changes in concavity, we might need to include in our analysis our POI. Now, how do we look for this POI or points of inflection? It's kind of similar on how we look for the critical number. We need this time the second derivative equal to 0 or the second derivative not to exist. So this time we're going to analyze the concavity of the function. Later on, we're going to combine analyzing the increasing and decreasing function and the concavity of a function. For now, let's stick with concavity first. So let's go with number 1 here. We're asked to determine the points of inflection and discuss the concavity of the function. So let's go with number 1. In number 1, we have, let's write it here. F of x is equal to x to the 4th minus 4x cubed. So what we need to do first is we need to find the second derivative to find the different points of inflection, because that's what we're just analyzing. We're not going to analyze if it's increasing or decreasing, only the concavity. So first, to find the second derivative, of course, you need the first derivative. So the first derivative of the function is 4x cubed minus 12x squared, while the second derivative of the function gives us 12x squared minus 24x. Yeah. So therefore, we're going to have, if the second derivative here is equal to 0, or the second derivative does not exist. That is a polynomial, so we cannot have it not exist yet. So we only have 12x squared minus 24x equals to 0. That's 12x, x minus 2 equals 0. So we have x equals 0 and 2. So from there, we now have this is our possible points of inflection, because remember, we are not sure if the concavity will really change after this. So if we are to analyze it using a table, we do something similar. We have the intervals, then a column for this time, the second derivative, and then the behavior. So using the POIs as our boundaries for the interval, so we have from negative infinity to 0, at x equals 0, 0 to 2, at x equals 2, and from 2 to positive infinity. So obviously at 0 and 2, the second derivative is 0. So let's just choose a number. For example, here we have negative 1. Let's use the factored form because it's easier to think of the sign in the factored form of the second derivative. At x equals negative 1, 12 times negative 1 is negative. Negative 1 minus 2 is also negative. And negative times negative, that's actually positive. So therefore, we'll have something positive here. From 0 to 2, let's say 1. 12 times 1, 12 times positive 1 is positive. 1 minus 2 is actually negative, so positive is negative. Negative. And from here, x equals 3. 12 times 3 is positive. 3 minus 2 is positive, so positive times positive, that's positive. So here, according to the second derivative test, if the second derivative is positive in this interval, then the behavior of the function is concave upward. According to the second derivative test, if its second derivative is negative, then the behavior here is concave downward. Here, concave upward as well. So as we can see, since there are changes in the concavity, then at 0, this is a point of inflection, and at 2, this is also a point of inflection. So as we can see, the analysis of concavity and the points of inflection is very similar in analyzing whether the function is increasing or decreasing on certain intervals. Let's have another example, the number 2. Now let's have number 2. Pause the video first and try to see if we're able to analyze the concavity and the points of inflection of this function. So I am assuming you already have. So just to show, the first derivative of the function is given by negative 12x over x squared plus 3 squared. And the second derivative of this was given by 36 times x squared minus 1 over x squared plus 3 cubed. So to find our possible points of inflection, let's put it down a little bit. It's either f prime of x is equal to 0 or f prime of x does not exist. And usually for rationals, for it to be equal to 0, it's the numerator that's equated to 0. For this not to exist, it's the denominator that's equated to 0. So solving this, that's x squared minus 1 equals 0. Then we have x is equal to positive and negative 1. For here, x squared plus 3 equals 0, but this has no real solution since it will become imaginary here. So therefore, our only possible points of inflection is only at x equals 1 and negative 1. So let's now create our table. We have our interval, second derivative, then the behavior. So we have from negative infinity to negative 1, x equals negative 1, from negative 1 to 1, at x equals 1, and from 1 to positive infinity. So this is already 0 here. So let's choose from negative 2 here, at x is equal to negative 2. So negative 2 squared, that's positive, minus 1, that makes it positive times 36, so that's still positive over, this is positive here, negative 2 squared is positive, plus 3 is positive, cube that is positive. So positive divided by positive gives you positive here. If we make it 0, so 0 minus 0 squared minus 1 is negative times 36 times negative. And here, 0 squared plus 3 cubed. This is positive, raised to cube, this is positive, so negative divided by positive, negative. And the other one at x equals 2, this is actually positive in the numerator, in the denominator, that's already positive as well, so positive divided by positive is also positive. So from here, the behavior at the first interval is called concave upward, in the middle concave downward, and in the third interval concave upward, making negative 1 upward of inflection and also positive 1. So that is analyzing concavity and points of inflection. But we also have another use for the second derivative. The second derivative can also be used to check on whether the given critical number is a relative maximum or a relative minimum. So we have here, if the second derivative at the critical number is negative, it's a relative maximum. It's somewhat of a switch. May I repeat that? If the critical number at the second derivative is negative, maximum. If the critical number at the second derivative is greater than 0, which is positive, it's a minimum. If it's equal to 0, the test fails. However, we're going to already see that when we combine everything and we use those behaviors we analyzed to sketch the graph of a function. But for now, we have covered analyzing concavity and points of inflection of a function.